Okay, let me continue as before. So it is surprising that this should be the case because, like, take for example, instead of having delta of C prime, we could have det C of prime. In the definition of delta, we could very well use another parameter, right? Like the degeneracy. And actually, for degeneracy, I was thinking about it the other day. It turns out that every class has a superclass of det C3. So it's surprising that this should hold, and yet it does. And we get this direction, one direction of this theorem we get from this guy, right? Because, well, let's say this holds, and let there be a proper minor closed superclass C prime of C with delta C prime equals 3. Then C must exclude an apex graph, because let's say it includes all apex graphs, but then C prime will also include all apex graphs. Then by this theorem, delta of C prime will be plus infinite, a contradiction. So how might we prove this guy? Just checking that the camera is recording all right. So how much will we prove this guy? Well, let's say that a proper minor closed class C includes all apex graphs and has delta k for some constant k. And well, right, and well, the argument is we will prove that it is not proper, so this will be the contradiction. And the way we prove it is not proper, so since it includes all apex graphs, it will include all pyramids, right? And so again, let's say, it includes this pyramid, where this is the grid. And just like before, sure enough, this means that it will include as a minor, we can contract every connected component corresponding to the pyramid. Once again, we will still include this graph as a minor. So we do not contract the apex vertex. And we will include we will include arbitrarily large pyramids. And the idea is that we will show that we will include arbitrarily large cliques, and because we are minor closed, this will mean that we will include all graphs. So how do we do this? So now this guy must have an edge towards every vertex here. And no single vertex can neighbor too many vertices of the grid. And well, there is a well-known structural theorem. It says that we have limited space, but there is a well-known structural theorem. It says basically that take a grid, right, and let's call the grid H. An H path is a path with endpoints in H, but no other vertex of H. So this path, the only vertex, it intersects H only on its endpoints. And let's say we have many such paths, non-intersecting one another either, so they are pairwise disjoint. Well, here is the fact. If we have n over 2 H paths on a grid, and this guy, H with the paths, will include Kn as a minor if the jump endpoints are far apart from each other. So there is some d such that if every endpoint has distance d or more, the theorem will hold. And we can use this to prove this guy. Basically, now obviously we can find, let this grid be, call this grid H once more. We can find H paths using this guy, right? We only need let's say we are not so lucky as to find it immediately. We start from here and we travel a bit, and we will be able to find, the vertex that neighbors this guy, let's say, and well, the distance will be large. The problem is, well, by taking this H path, we may lose other H paths, right? Again, H paths must be vertex disjoint, and we can no longer take this H path, for example, as a result. So the way the argument works is that, well, look, we include all pyramids as minors, right? So let's take some super large pyramid. Basically, if we have a large enough pyramid, then, this connected component, its vertex on it has maximum degree k, and it must neighbor all the vertices in the grid. So as the grid gets large, necessarily this this connect component has more and more nodes. The inflation of the apex vertex, and has more and more nodes. And so we have a connected component, a subgraph, with an unbounded number of nodes and bounded maximum degree. But this means that it will have unbounded diameter as the grid gets, as we choose a larger grid. And we can take a maximal path inside the vertex, the inflation, and basically by tweaking, so this will have some subtrees here, and by tweaking the maximum path, and by contracting on the subtrees here, we can find a path where each vertex will have some edge down here, which before was not the case. And so every two vertices will form an edge path, and then we just need them, and we have an unbounded number of we will have an unbounded number of such edge paths. So we hit n over 2 for all n, and the only thing left to request is that they are far apart enough from each other, and we can do that. In fact, we can demand that we can request basically that we can choose the placing of the endpoints so that this holds. And in fact, this is funny. We can, let's pick some arbitrary subset of the apex graph. As the apex graph gets larger, and let's have the arbitrary subset also get larger together. So we get larger and larger subsets for larger and larger grids. We can demand that the jump end, that the edge path endpoints fall only into the subset. So we can pick a larger and larger subset such that every vertex in it is distance from every other vertex in it. And it's funny. So this is the general high-level overview of the theorem. And it's funny, we can actually demand that this a whole bunch of stuff for this apex vertex, like inflation of an apex vertex gives us all sorts of freedoms. Like we can also pick an ordering of the subgraph and say demand that every 10, let's say, vertices we find an endpoint, an edge path endpoint, and in the next 10 vertices we find the next endpoint of the same edge path. And it's funny, we aren't even using that, we have a grid. So this holds, basically, this holds because of the inflation of the apex vertex. So even if we had some other graph here, as long as it got larger and larger, we could find edge paths and have them fall wherever we want, approximately, and have them come in any order and frequency we want. So that's nice. So here is a last thing I would like to say. And by the way, the other side of this theorem is proven. Oh, sorry about that. Okay, now this is fixed again, I think. And the other, the other side of the theorem, I'm not going to get into that, but basically it uses strongly k-almost embeddable graphs. You can think that, it's the same trick as in k5 minor free graphs, where we take the high level, we take the embeddable part of the k-almost embed, we take, the graphs it decomposes, the graph of 4 bytes decomposes into, like strongly k-almost embeddable graphs. For the embeddable part, we do exactly the same thing as in planar graphs, and we also make sure to, just like in k5 minor 3, we retain the clicks. In this guy, we will retain the clicks that are necessary for the click sums, and then it's the same idea, and we will make sure to do it in a way that the minimum degree stays close, and after doing the click sums we can regain the original constructed graph, constructed by click sums graph as a minor. And we do the same thing for the apex vertices and for the vertex vertices. It's a big argument. So, here is the last thing I would like to say. Remember that form k3,3 has maximum degree, has delta 4, right? This means that every graph in it is a minor of a graph with maximum degree 4. Now it would be nice to ask ourselves, let's say we take this class and let's restrict it into a class of delta 3. How? Take all graphs of all graph Z of form k3,3 of delta of Z less or equal to 3. Let this be some class, I don't know, call it A or something. And then let's take the minor closure of A. So let's denote the minor closure of a class like this. What can we say about this class? So every graph in it is a minor of a graph of maximum degree 3, right? So it has delta 3. We also know it is a minor closed class by construction, and we also know that it is a subclass of form k3,3. So when it was a nice thing to notice that it just so happens, and in this manner we can start defining all sorts of minor closed classes about which we don't know much. It was nice to notice that this is exactly the planar class. then I started saying, okay, we created a minor closed class in a kind of natural manner, and we got a natural answer as a result. So let's do this again, but with 3 width. Remember that delta of 3 width is equal to the graphs of 3 width less or equal to k have delta k. Sure. Let's take this class, denote it like this, and again take all graphs. Now as a reminder, this graph has delta k, and take all graphs again of delta of z less or equal to 3, let this be A, and take the minor closure of A. What do we get? Well, in 2009, in their paper that proved that the delta of this guy isn't 3, Markov and Xi also showed that this class, they didn't define this class actually. What they did say was that if we take the class of graphs of 3 width less or equal to k, and we restrict it to the graphs of degree at most 3, we will still contain S minus all graphs of 3 width k minus 1 or less. Right? So, basically, this means, okay, they proved this, which means that this class, by definition, includes all graphs of 3 width k minus 1 or less. And also, it is included in all graphs of 3 width k, and both inclusions are proper. So we have a minor closed class between those guys. We have defined it in a natural way that seems to give us a natural graph class path. And we know that there are many interesting variations of 3 width, right? So a natural thing to ask is, well, is this also a natural variation of 3 width? And there is another class that the class of graphs of simply 3 width less than or equal to k is also in here, has this property. So I looked into this, and the conclusion was that those classes aren't the same, but it would be nice to show that this has a natural interpretation. I was looking into it a bit, and actually it's very easy to find its forbidden excluded minors, given that we know those of 3 with less or equal to k. You only need to take in a high level way, we only need to take the graphs that we will still retain, we can contain any minor we had here. And for this one we have to also exclude all graphs that don't have a super minor of degree more than 3. That don't have a super minor of degree 3, sorry. Which are pretty easy to see. Generally they are, I was thinking of that the other day, and a few months ago, I didn't sit to. And Markov and C say that it would be interesting to find the forbidden minors of this guy basically. And you can find them easily. They are, so we can even find the forbidden minors of this guy. And they are approximately, take this to be a graph of k plus 1 vertices. And for every k vertices, take another vertex and connect it to all of them. And those generally variations of this guy, like maybe you can have many or few vertices here, you can have between those guys many or few edges connecting them. It will be, we will have, those will be the forbidden, extra forbidden minors that need to be added. And it's nice that, and in general, I think that we can always, doing this kind of restriction, if we know the forbidden minors of this, we can easily find the forbidden minors of this. And in a field where it's very hard to do things like find the forbidden minors, was it the graphs of genus 1 that we still don't know all the minors about? Maybe someday we can start from a graph whose forbidden minors we know. And again, this is a high level overview, I don't expect you to get everything, but maybe we start from a graph whose forbidden minors we know, and doing those kinds of class creating operations, we can reach a class such as the class of graphs of genus 1. And then we will be able to find a nice description of its forbidden minors. So thank you for listening to my talk. It's been a long day. I was faster in the morning, but I appreciate you listening to me, and I hope you found some of the things I had to say today interesting.